All right, it is Wednesday, everyone, and we, dun 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 dun, are starting the unit you've been waiting for in AP Chemistry, the last unit. And what this is a further application and discussion of thermodynamics. Entropy is the word of the day. And as a review, we talked about enthalpy, with the TH in there, as loosely meaning heat, and delta H, and those types of things. So those will kind of come back to you as we talk about this. So what in the world is entropy? Well, it's a measure of the disorder and randomness of a system. Okay, matter becomes spread out. All right, and one of the things we're going to do for our evaluation here, like I said, we're just going to have good notes. So to make sure that you're actually listening to the lecture, I'm going to give you some specific instructions on certain pages. Like on this one right here, I want you to circle or highlight this statement right there, and a positive value for delta S is favorable. So you're going to highlight both of those things. And also, you know what? I want you to highlight just this one, but not the second one. So I'm going to check you. Did you do the first one, the third one, and the fourth one? Yeah, that's right. You gotta listen to me. All right. Okay, let's try the next slide. These are some examples in your house. Kind of silly. Next slide. You didn't have to write anything on that one. You can write it's kind of silly if you want. This is important. All right. The laws of thermodynamics. The first one says energy cannot be created or destroyed. And I want you to write that as a rewording right there. Cannot create or destroy energy. It has to be contained. You can't. It's the same thing like the law of conservation of matter. Okay? So that's the thing I'm going to check for on this page, right there. Now, the second law of thermodynamics is this one. Circle this and start. That's what this whole chapter is all about. The entropy of the universe is constantly increasing. There's overwhelming evidence that the entire universe is spreading out and going away, and there might have been some big bang at the beginning that started this. But it is a driving force in nature. There is no mistake about that. Now, as a small homework assignment, I want you to try this. The next time that your parents say something like your room is messy, I want you to say, do you know anything about the second law of thermodynamics? The disorder and randomness of the universe is inevitable. You cannot fight it. If you look at my desk, you will see that is a true statement. Okay? So see if it works with your parents. I'd like some feedback on that for an assignment. Now, this next one is important because it gives us some idea on a chemical level. What are the things where the change in entropy will be greater than zero? Okay, or you'll get more randomness. Melting, highlight that one. Highlight vaporization. Now those two processes, if you think about melting, you have a solid going to a liquid. And this second one is more random, so that's an increase. Vaporization, certainly you have molecules in the liquid form breaking free and going to gases, and then they're all over the place. Okay, so that's important. So you're gonna highlight those first two things. Just getting more particles, so right there, just circle that. More particles, if they're in the same state, tends to be more random. It's chaos. It's crowded. Okay. Making solutions, highlight that. Adding heat, or increasing the volume of a gas gives those gas molecules more chance to move around. So really, you're highlighting everything on this page because that's what it's all about. It's not about this silly slide over there, which may give you some concepts of these things, but it's really it's about this. Okay, so there's your nice picture of solid water or ice going into liquid water, which is less ordered and less organized. So small s on the left, large S on the right. Okay, so here's what you have to do on this slide. You have to put the name of a teacher who has a very organized room and desk right there. Can't be me. I know you were thinking Chalmers, of course. This is going to be fun for me to see. Organized desk, disorganized. All right? So a less organized desk. Name of a teacher right there. That's the things that have to be there. So-and-so's desk, so-and-so's desk. Okay? Do it. All right. And of course, vaporizing, also the same thing, even more so when that's happening. All right? Now, if you look at what you have right here, so this example, if you look at this chemical reaction here, 4 molecules of a liquid on this side, and over here, 6 plus 12, 10, 29 gas molecules on the right side. Chaos on the right side. Delta S greater than 0. All right? So that is a really good example of this. Okay? So just circle this statement right there. Okay? Or highlight. Circle or highlight. Okay? This is sort of just repeating the same thing. So just take a look. It's a nice little picture from solids to liquids. Now this one is interesting. When a gas gets dissolved in a solid, then you have delta S will be less than 0. Okay? And this is where people get in a little trouble in this unit, is the double negative thing. Because if you're saying entropy will decrease, entropy is disorder. So there is less disorder, which means more order. Okay? So sometimes if you could think of it as becoming more order, that is when delta S is less than 0. And these are more organized here because these gas molecules are all over the place. It's chaotic. Highlight that word to prove you're listening. You still with me? Chaotic, right there. Okay. This is a good example of the whole process that we just talked about. As you add heat, these become more and more and more random or disordered. Okay? And on this slide, I want you to draw something being stabbed by this arrow. That can be anything you want, a person or an animal, or depends on the mood you're in. But something, you're going to do a little drawing right there of something being stabbed by that arrow. Still paying attention? I will find it. Okay. You've seen this diagram before. Is a Boltzmann distribution. We had talked about this in our previous thermodynamics unit. Obviously, as temperature increases, there's more and more kinetic energy, but there's a wider dispersal. We talked about a little bit about standard deviation in our last lab. This one has a much higher standard deviation. They're all over the place. So two things happen. Their average is higher and their standard deviation is higher as you increase energy and randomness. Okay? If you were to increase the volume of a container, as we mentioned, it just gives those gas molecules a chance to be even more random. And then this is the last thing that we're going to do. This is actually a nice little short lecture here for you today. If you take a look at this, this is in your purple sheet, and it should seem familiar to you. The sum of the moles of, in this case, entropy of the product. What's missing is the little delta symbol. So that's on your purple sheet, and you'll be able to find that. So we can use this in solving problems like this, okay? So I did attach the thermodynamics quantity worksheet. I'm going to switch over to that really quick here. So this guy will feel very familiar to you. We did these delta heat of formation reactions in kilojoules per mole, and you can see there's our entropy values. So we can find in the problems that we're going to do, they're talking about gaseous water, and there's the value right there. So, but one of the things is very important to note. This is kilojoules. This delta G, which we're going to get to later in this unit, is in kilojoules. And look at the entropy, joules. It's just not as big of a factor as heat is in thermodynamics. It's important, and it will affect results, but the numbers are smaller, so they're always given in joules. And there is no delta. You don't talk about change in entropy. Entropy is just a state. You're like, this is a mess. You don't talk about what it was before or whatever. Okay, so I just wanted to make a quick reference to that, and then we'll head back to the lecture here. Okay, so this is where we left off right here on this slide. That's the equation given to you on your purple sheet. Now this next line, okay, here's one of the things that I was going to test. Do not write this line. This is not necessary. It's simply showing, what products and reactants are. So let's just jump right into plugging it in. It's kind of like, a density problem. There's your equation, there's your formula. So you know where these numbers came from. We just found them. If you do the problems, you'll see that they vary a little bit. Our sheet said 304.3 for this one, for instance, 191.50, and this one was the same. But you just subtract products minus reactants, and then they're either going to be positive or negative. So here you got a delta, negative is minus. So there was an increase in entropy in the system. Okay, so a negative. So this would be kind of nature would favor this kind of process. Okay, so and then we'll do this one again. Don't write that line. Look at all those ugly parentheses. It's just weird to do this. So just plug the numbers in. Again, these numbers will vary slightly, and just get those recorded. And I think this one was 188.83 on your sheet, and then this one was 69.91. We'll do some more of those problems on the next one. But then remember the final unit, joules per Kelvin mole. Okay, And make sure that you got that on the previous one too. I forgot to mention the unit. Joule per Kelvin times mole. All right, that's it.